So our second question here says a canoeist leaves a dock and paddles her canoe at an angle across a river. The current is flowing at 3 kilometers per hour. The resulting velocity of the boat is 5.4 kilometers per hour downstream in a direction that forms a 15-degree angle with the adjacent shore. Determine the canoeist's velocity relative to the water. So we're given velocities here. We're given the velocity of the, let's do this in green, the velocity of the water relative to the shore. We're given the resulting velocity. So this is the velocity of the boat relative to the shore. And then we want to find the velocity relative to the water. So let's sort of come up with symbols to represent these things. We'll call W the water velocity. That's how fast the water is moving. So that's basically the current. We will call B the boat's velocity. Okay? This is the velocity of the boat relative to the water. And we'll call it the boat velocity because it's sort of the velocity of how fast the boat can move if the water was completely still. And then we're going to add the two of them together, and we'll just call that the resultant velocity. You might be tempted to use C as a vector in there, but then it gets kind of confusing because does C represent the current or does C represent the canoe? So it's best to just avoid C altogether in this question. Okay? So let's draw ourselves a picture here of what's going on. We've got a river, and we'll make the river blue because that's kind of fun. And then we've got our canoeist leaving the dock and heading at an angle across the river. So if we make this a little bit bigger to give ourselves some more space, canoeist starts right here at the dock, starts heading out across the river. So we'll say that this is the path that the canoeist takes. So this is our B vector. Okay, that's the boat's path, or the path that the canoeist intends to take. We're told that we've got a current flowing at 3 kilometers per hour. So that is going to be our water velocity. And I've made the current going like this. So what's going to happen is that the resultant velocity, the path that she actually takes, is going to be the vector sum of the boat's velocity, the path that she intends to take, plus the way that this current pushes her around in the water. Okay? She wants to do this. The current gets added to it to produce something other than what she intended to do. So if our current is coming along like this, we need to add it onto the boat's velocity, and then the vector sum of those two, I've got them tip to tail, is going to be our resultant velocity. Okay. Now we're given some information about this resulting velocity. The resultant velocity of the boat is 5.4 kilometers per hour, so that's the magnitude. And we're given some information about the direction, in a direction that forms a 15-degree angle with the shore. So we're told that this angle in here is 15 degrees. What other information are we given in the question? We're given the current is flowing at 3 kilometers per hour, so we're given the magnitude of that water velocity up here. What do we want to find? Well, we want to find this B vector right here. That is the canoeist's velocity relative to the water, so we want to figure out both the magnitude and the direction of that B vector right there. So, how can we do that? Well, let's see. We know this angle here is 15 degrees. We know that the current up here is parallel to the shore, so that means that this angle up here is 15 degrees as well, because they form that little Z pattern. So now I know the length of this top side here, the length of this side down here, and I know the enclosed angle between them. So I can use cosine law to find the length of this third side. So if we do that, that tells us that the magnitude of b squared is going to be, let's see, 3 squared plus 5.4 squared minus 2 times 3 times 5.4 times the cosine of 15 degrees. And we can just punch this into our calculator, take the square root, and that gets us 2.62 kilometers per hour. Okay. We also want the direction. So that's our magnitude. We need our direction. For our direction, we always want to find an angle that is close to the tail of our vector. So we're looking for vector b here. Our tail is down here. So we want to find that angle in there. It's got to be an angle inside the triangle. It's got to be close to the tail of our vector. So how can we find angle theta here? We could use sine law, okay? But I'm not going to, because there's a possibility that I've drawn this diagram completely wrong, okay? It doesn't tell us in this question whether she had sort of, how can I draw this? Whether b is supposed to be as I've drawn it, or b is supposed to be out this way like this, okay? So I don't really know how big that angle theta is supposed to be. Okay? And when there's a possibility that I might have misestimated the size of an angle in my vector diagram, I don't want to use sine law, because if there's a chance that that angle is actually bigger than 90 degrees, sine law won't pick up on that. So I'm going to use cosine law here, which doesn't have any problems with angles bigger than 90 degrees. So, using cosine law, cosine theta is going to be 2.62 squared plus 5.4 squared. Those are the magnitudes of the two sides on opposites on either side of our angle theta. And then we subtract the side opposite squared, so minus 3 squared, and divide the whole thing by 2 times 2.62 times 5.4. We punch all this into our calculator, and we get that theta is 17.2 degrees. Now we're not quite done. The original angle that we were given in the question was measured adjacent to the shore, from the vector to the shore. So when we specify the direction of our of her path here, we want to do the same thing. So we want to take our angle here, our theta, add the 15 to it to get the angle between B and the shore. So that's sort of our final step here. We take our 17.2, we add the 15 degrees to the shore, and we get 32.2 degrees. And then we sum it all up, putting magnitude and velocity together. We can just say something like the magnitude of B, vector B is equal to 2.62 kilometers per hour. And then our angle is going to be 32.2 degrees to the shore. So we've got magnitude, and then we've got direction.